Next talk is by Rakesh Vohra, who's a professor of economics in Kellogg Business School at Northwestern. And he's going to talk about programming, mechanism design, Poly Metroids, and all this other fun stuff.
Thank you very much, Ariel. If you're disheartened by the fact that there is a number 47 on the lower right-hand side of this, of what you see here, that's 47 over the 2 sessions. And I am not really wedded to getting through every single one of them. My preference is actually to do less, because sometimes less is more. So you should feel free to ask questions and interrupt at any time. Okay? And I think I'll give Ariel a copy of the slides to distribute subsequently. So you really don't even have to take notes because you'll get these in a moment. Okay, so let me begin with a brief introduction about what mechanism design is. So I'm going to view it as essentially a problem of optimizing the allocation of resources, but where's the difficulty? The difficulty is that the parameters that you need for the optimization problem are privately held by the agents, and agents will be reluctant to reveal those parameters because those parameters determine the utility that they'll enjoy from a particular allocation. So the central challenge for the planner who's solving the optimization problem is to simultaneously optimize the allocation of resources and elicit the information needed to make that allocation from the agents. Okay? And the usual method for doing this is you have basically carrots and sticks, which is your carrot is the allocation that you're going to choose, and the stick is usually monetary transfers. But in the example that I'm going to use later on today, it will not involve monetary transfers at all. Rather, I want you to get around, and the reason I want to do that is because I'd like to inspire you to think about other kinds of carrots that are different from money. Many mechanism design problems, I've said before, are optimization problems, and what I could do is I could give you a long list. Here's just a short list, and that's all I'm going to say. Here's what I want to do for today. Today, I want to show you how Poly Metroids arise naturally in mechanism design problems and why they're useful. If there's time, I'll also talk about the presence of shortest path problems. And then tomorrow, I'll talk about the use of what's known as iterative rounding as a way to develop allocations in settings where there are no monetary transfers. So that's my plan. As I said, I'm not wedded to getting through everything, so feel free to ask questions and stop me at any time. Okay, so first, since roughly about 80% of you are either in your first or your second year, that means you probably haven't seen anything about submodular functions or Poly Metroids. So what I want to do first is define what submodular functions are, give you some examples of them, then describe what a Poly Metroid is, and then talk about the problem of maximizing a linear function over a Poly Metroid, and then I'll put that to use in a particular mechanism design problem. Okay? So let me first define submodularity. So capital E is a ground set of objects. You could think of those objects as being perhaps a set of vectors, or the set of edges in a graph, or indexing a set of events in a stochastic system. Okay? I'm going to define a real valued function on the subsets of E. That's called little g. And I want this function to have 2 properties. The first is that it should be non-decreasing. In other words, as the set gets larger, G of that set should not go down. Okay? And then the second condition is this, and this is the submodularity condition. Now, if you're wondering at all why this is natural, think of G as the probability and S as an event. Then if you think about the usual rules of probability, it satisfies this condition. In fact, it satisfies the stronger condition with inequality replaced by equality. Okay? Now, an equivalent definition of submodularity is this. Take 2 sets, one contained in the other. So here's S, and here's T, which is larger, which contains S. pick something that's outside of T, that means it's also outside of S, then this difference is smaller than this difference. Now, if you look at this object, you can interpret it as a sort of derivative, and what it's saying is that the derivative gets smaller as the set gets larger inclusion-wise. Right? Now, for this reason, submodularity is sometimes thought of as an analog of concavity. So here I want to give you a warning. While submodular functions share some of the properties of concave functions, they do not share all of the properties of concave functions. Right? There is a separate literature devoted to what are known as convex extensions of submodular functions, which suggests that submodular functions actually sometimes have some of the properties that we associate with convex functions. Okay, now, why are submodular functions useful? The answer is they crop up in the oddest sorts of places. So let me start with the first example. The ground set E is a finite set of vectors in Euclidean space. The function g of S is simply the rank of the set of vectors in S. Now that's a submodular function. Now, one way to see why it's got to be submodular is this. If this difference is 1, that means the vector j is not in the span of T. Agreed? If this difference is 1, then this difference also has to be 1, because if j is not in the span of T, it can't be in the span of any subset of T. And if j is in the span of T, this has got to be 0. But this could be 1. Okay? E is a finite set of vectors, and g of S is the log of the volume of the set spanned by those vectors. That also happens to be submodular. Let E be the set of columns of a non-negative, actually should be non-negative definite matrix, and G of S is the log of the determinant of the principal minors associated with S. That also happens to be submodular. E is the edge set of a graph, and G of S is the size of the largest acyclic subset of S. That's also submodular. E is the vertex set of an edge-capacitated network with a distinguished source vertex, and G of S is the maximum flow into S. That's also submodular. E is a set of events. G of S is the probability that all the events in S are realized. G of S is what's known as supermodular, which means the negation is submodular. Right? And the entropy of the joint distribution of a bunch of events is also submodular. Okay? So the point of this list is to say submodular functions arise in all sorts of places. You should keep your eyes open for them. Okay? And here I'm simply going to point out in this session today how submodular functions arise quite naturally in certain mechanism design problems. Okay? Now, what's a Poly Metroid? It's a polyhedron. I've defined it at the top. So it's the set of vectors x such that sigma of xj, j in S, is less than or equal to g of S for every subset S of the ground set. So notice a Poly Metroid is described by a number of inequalities that is exponential in the size of the ground set. So at first glance, that may seem a rather horrendous object because it's very large, but that should not deter you. And the reason it shouldn't deter you is because optimizing over that object can be done using a greedy algorithm. Okay? Now let me motivate why you shouldn't be surprised by that. Supposing the ground set E was a set of vectors in Euclidean space, and G of S was the rank function for any set of vectors. Okay? Now if I asked you, find me the largest subset of linearly independent vectors, and this is a question that you should remember from linear algebra, you know how to do that. If you think about it, that polyhedron describes, if you like, the convex hull of the set of all linearly independent vectors. Okay? Now, what's the algorithm, what's the proof that you learn in linear algebra for finding the largest collection of linearly independent, the largest subset of linearly independent vectors? Pick a vector, then pick another one. If it's not in the span of the first one, keep it. If it is, throw it away. Then pick another one. If it's in the span of the set you picked, throw it away. If it's not, keep it and proceed. Okay? Now, if you think about it, that's a fairly straightforward greedy algorithm. Now let me add a variation. Supposing every vector came with a weight. So I don't just want the largest linearly independent subset, I want the largest weight linearly independent subset. What would your conjecture be about an algorithm for that? Pick the vector with the largest weight, pick the vector with the next largest weight, provided it is not in the span of the vectors you've already picked. Okay? Well, it turns out that idea works for any submodular function. And so here is a description of the greedy algorithm for maximizing a linear function over a Poly Metroid. So take the elements of the ground set, order them from largest to smallest. Okay? K is the threshold that corresponds to the last objective coefficient that is non-negative. Okay? Start initially with the, so let me let Sj be equal to this and define Xj this way. G of Sj minus G of Sj minus 1. Now think about the rank function. If J is not in the span of Sj minus 1, then this object is 1. So you pick the vector indexed by the letter J. If J is in the span of S super J minus 1, then this object is 0. That means you don't pick that vector because it's in the span of the vectors you've already picked. Okay? And for any variable whose coefficient is negative, you set it equal to 0. Okay? Everyone with me so far? Okay. Okay. So what's the next step? Let's prove that this indeed gives you the optimal solution to the linear program. So reminder, we're maximizing Cx, a linear function, subject to the Poly Metroid constraints. Actually, let me think, yeah. So over here I've written down the Poly Metroid for the case when the ground set consists of just 3 elements, 1, 2, 3. And we want to maximize Now the first thing we should check that this actually produces a feasible solution. Agreed? Well, C1 is larger than C2 is larger than C3. So we start with X1, and we want to make it as large as possible. Well, there are 3 constraints that upper bound X1. This one, sorry, there are 4. Now, of these 4 constraints, the one which gives us the tightest upper bound is this one. Agreed? Now, where does that come from? That's the monotonicity assumption. Right? F1 has to be smaller than this, this, and this. So the largest we can make X1 is equal to F1. Everyone with me so far? So that constraint now becomes tight. Now, if I've set x1 equal to f1, then I move it over to the right-hand side. Okay. Now we go to the next variable. We want to make it as large as possible. Well, the next variable is x2. Notice x2 is upper bounded by this. It is upper bounded by this. And it is upper bounded by this and by this. Now, which of these is the tightest upper bound? It's no longer this. Why? Because this is smaller than this. I'm sorry. This is smaller than this. Right. Okay. And how do we know that? That's the submodularity assumption. So this is really the next upper bound. So we set x2 equal to this. Right. Then we take x2 over to the other side. So I'm going to run out of space here, so I'll just put that there. Now, the last variable that's left is x3. The constraint that's going to determine the value of x3 is this one. Okay? So that's what we're basically doing here. So another way to think about the greedy algorithm is you're starting with a variable with the largest objective coefficient. You're making it large as possible given all of the constraints, moving it over to the right-hand side, and repeat. Right? Now, is that enough of a proof of feasibility? You need to show it's not, so if but remember, we assume that the F's or the G, I switched notation, F should really be G. I said that's monotone, right? So given it's monotone, these are all going to be non-negative. Everyone happy with this? Say again? But haven't we taken that into account given the way that we chose the variables? Everyone happy? Yes?
Do you have to worry about the empty set?
Well, so let's make life simple and assume all the coefficients are positive. So, so in that sense, okay, let me back up. So what's your concern with the empty set?
When you have 0 less than or equal to something.
I have 0 less than or equal to Okay, so if S is the empty set, then on the left-hand side I've just got 0, which was just another way of saying that the submodular function has to be non-negative, right? So I should have said, let's assume that the function has non-negative value. Yes?
You have to show that x1 is larger than x2 larger than x3. So that's again, that follows from submodularity.
Okay, so why is that needed to establish feasibility?
Feasibility for its maximum.
So that's a separate question. So at the moment I just wanted to say, first thing we should do is show that that solution is feasible. Right? So I went through some steps of the algorithm. And I'm asking you whether these steps are enough to prove feasibility. Yeah? Okay. So, okay, fine. Sorry. So we've got feasibility. Now the next step is optimality. Okay? How are we going to do optimality? Well, there are a number of ways to do optimality, but let me hint at the way you would do it. notice this procedure tells us which constraints bind. Agreed? That means we also know which constraints don't bind. Okay, so complementary slackness will then allow us to say that for the constraints that don't bind, the corresponding dual variable should be 0. Agreed? So the only constraints really that we should be worried about are the ones that we use to fix the variables. So this one, this one. No, I'm sorry. Which one? This one here. This one. Right? Those were the only constraints that were binding in our solution. Let's write out those particular constraints. The others could be binding, right? But so as we're being informal rather than formal, we'll say, well, the ones that didn't turn out to be binding, let's just hope that they aren't. Okay? And so our guess is, so let's write down the ones that were binding. Now you'll notice this is, what is it, upper triangular? Right. So the dual variables, remember, correspond to each of these constraints. Now, how do we find the dual variables? The answer is flip to the transpose of the matrix of binding constraints and solve for the corresponding lambdas. Now, because it's upper triangular, there's a very easy way to find the inverse of an upper triangular matrix. If you think about it, what was the greedy algorithm doing? It's essentially going through the steps for finding the inverse of the inverse of an upper triangular matrix. What do? You start with the element at the bottom, make it equal to the right-hand side, take it over to the other side, climb up, go to the next one. Okay? So the last step in the proof is solve the dual system, okay? And then check that your solution to the dual complements the solution you have for the primal. Okay? And that's a proof of that the greedy algorithm is optimal. Does that make sense? Okay. Now, all I care about is that there is a simple algorithm for solving the following problem. Maximize a linear function subject to a Poly Metroid. What is that algorithm? You assign priorities to the variables. You go to the variable with highest priority and make it as large as you can. Then go to the next highest priority variable, make it as large as you can. Stop when a variable gets no priority. In other words, its coefficient is negative. Does that make sense? Okay. Now, the other interesting observation, sorry, yes, go ahead.
Sorry, in the statement of your problem, are there any constraints on G other than its real value function?
With the so I'm using its non-negative, monotone, submodular.
That's it.
That's it, okay?
Also setting a G of the empty set equal to 0.
Yeah, so, okay, so, yes, so G of the empty set is 0, right? Now, you can actually drop one of these. You can drop monotonicity, okay? The reason you can drop monotonicity supposing monotonicity was violated, in other words, this was larger than this. Agreed? Now, if you think about it, it essentially means this constraint is redundant. So you can always replace this by this. Okay? Okay? Now, this, what I just did, is there's a procedure for it. It's called replacing the submodular function by its monotone cover. So the answer is, if your original submodular function is not monotone, replace it by its monotone cover, and then run the greedy algorithm.
So you mean then that submodularity is not a condition that's required?
No, submodularity is the condition that's required.
Here you're replacing the...
Here I wanted to get monotonicity, right? So I was saying you can, monotonicity, in other words, I assume monotonicity up there. My point is, I didn't have to assume monotonicity. if I see a violation of monotonicity, I replace the submodular function by its monotone cover. Okay, then I have, and that preserves that operation preserves submodularity, and now just run the greedy algorithm on that. Yes?
But if the value of S itself, or the optimal set value is monotonicity, then don't you find some, so the sum of the x's in S is larger than, so it's still smaller than the monotone, the value of the monotone cover, but it's larger than the actual value of G.
No, I don't see, so this constraint, so if there's a violation of monotonicity, this constraint is implied by this, agreed? Right? Because this is a tighter constraint than this one. So that means this constraint is essentially redundant. Equivalently, I can always shrink the right-hand side down to this. I don't change the optimal solution. Okay? Okay. Now, one other thing you get from this is that you also implicitly get a description of every extreme point of the Poly Metroid, which is every extreme point of the Poly Metroid can be described in this way. Pick a priority ordering over the elements, and then run the greedy algorithm with respect to that priority ordering. That gives you an extreme point. Does everyone see why that's the case? Because every extreme point of a linear program is characterized by it being the optimal solution to maximizing some linear function over the polyhedron. And the only information we use from that linear function is the ordering of the coefficients. Nowhere do we use any information about the actual magnitudes. Right? Okay.
Sorry?
Yes.
Sorry to be nitpicky. Going back to the monotonicity thing.
Yes.
Finding the monotone cover, isn't it potentially exponential term? Because I might need to look at all possible...
Potentially, yes. I haven't given it much thought, but I don't care about that. Right? So,
Well, you took a lot of time caring about not writing exponential term when you're doing the actual solution, right?
but so you're right. So how should I answer this in the best way possible?
Did you get a fine?
No, I think it's a perfectly reasonable question. Okay.
Care about differences of one.
No, because the functions I have may not be integer valued. Right. So here is the answer to your question. Right. Why is looking at Poly Metroids? Let me hold off. And the next slide I'm going to put up will allow me to answer your question. Okay. This is the so what. Why do I care about maximizing a linear function subject to a Poly Metroid? And the answer is, for economic applications, we're not interested in simply knowing whether an optimal solution exists. Okay? Because if you think of mechanism design problems as an optimization problem, the moment I write down a formulation of the optimization problem, I'm done. That cannot be interesting, right? What's interesting is we want to be able to say something about the qualitative properties of the optimal solution. So this is where Poly Metroid optimization problems are useful. Because they can be solved using a greedy algorithm, that allows you to say something qualitative about the nature of the optimal solution. Does that make sense? Okay. So now, let's go back to the issue of the monotone cover. The fact that you've given me a submodular function that is not monotone doesn't concern me, because I could replace it with its monotone cover, and then I know the greedy algorithm works, and so I can still, in principle, say something qualitative about the nature of the optimal solution. Is that okay? So I want to illustrate this now with a particular application. And here's the application. It's inspired by a paper by Ben Porath, Eddie Deckel, and Bart Lippmann. There is a single good to be allocated to an agent, to a set of agents, and you want to allocate it to the agent with the highest value for that good. Okay? Now, the value that an agent assigns to that good is private information of the agent. Transfers are not permitted. I'm going to assume that my agents are risk neutral. The value that each agent assigns to the good, I'm going to call their type. I'm going to assume that types are independent draws from a discrete set. F subscript t is the probability that an agent is of type t. And I'm assuming that each possible type occurs with positive probability. That's not essential, it just makes everything convenient to write down. Now, the added wrinkle is this: for a cost k, the planner can verify an agent's report of their type. Okay, what setting is this supposed to model? Well, let me give you an example. I make no claim that this is at all a realistic example. I wanted instead an example that I could plausibly describe in a couple of minutes, which would be rich enough that it would be interesting to look at. So imagine I am the dean of a large school, and I have funds sufficient to fund a single faculty position. There are many departments competing for the funds for this one slot. I cannot use transfers. Why? Because within the school, money is really funny money. Money that comes from the department goes back to the dean then eventually hands it back out to the departments. Okay? But what I can do is I can inspect the reports of the departments. So a department can come to me and say, we have a fantastic candidate. For a cost, I can inspect that claim. Now, I'm assuming here that inspection is perfect. That if I choose to invest the cost of inspection, I will be able to tell whether the department misreported or not. And the other crucial assumption that's being made is that the utilities or the values that departments assign to the faculty candidates are commensurable. In other words, it is possible for me to rank the claim of Department X with respect to Department Y in a way that everyone universally agrees on the ranking. Right? So in a sense, this assumption here that there is this thing called a value and everyone agrees on what the value is, that's the problematic assumption. Because it allows me to compare, rank faculty slots across departments. Okay? But that's the example. Right? So notice, I don't have monetary transfers. The only stick, if you like, is inspection. Everyone with me so far? Now, the first thing you might think of is, well, just have everyone tell me their type and give it to the department with the highest reported type. Now, this, of course, is problematic because every department has an incentive to say, our faculty candidate is the best possible in the world. Not just this world, but in another universe as well. Okay, but you have a stick, and the stick is you can threaten to inspect. Now, if you inspect and you discover that the department has lied, the obvious punishment is you withhold a slot from them. Does that make sense? Okay. Now, you can see an obvious difficulty. What if the value that the department is claiming for the slot is far less than the cost of inspection? Yes?
So who bears the cost of inspection? It's you, right?
The dean bears the cost of inspection.
So then they still will all just lie, right?
Well, the answer, well, no, the thing is, remember, if I inspect and I discover that you're lying, then I withhold the object from you.
I mean, so you withhold it even if he was actually the highest value, but I lied?
I might have to do that, right?
I see, okay.
Yeah. Okay, so, okay. So then the other trade-off you worry about is, what if the cost of inspection is 10 and the value claimed is 1? Do you want to inspect? Now, if you don't inspect, what's the risk you run? A lot of people will say our value is 1 because I know you're not going to subject me to inspection. But then you might say, well, maybe that's not a problem because if a whole bunch of people say their value is 1, one thing you could do is then randomize the allocation of the slot. right? Okay. So, as I said, you can now start to imagine lots of different schemes, and at least what I want to convince you of is it's not immediately obvious what the right scheme would be. Okay? So let's do this a little more formally now. So let's restrict attention to what are known as direct mechanisms. What is a direct mechanism? I, as the dean or the planner, I'm going to announce 3 functions, and the arguments of each of these functions is the profile of reported types. So one function is an allocation rule, which is going to specify what fraction of the object goes to each agent as a function of the reported type. Now, if you're worried that I'm talking about a fraction of an indivisible object, interpret the fraction as a probability. Okay? The second function is a payment rule, specifies the payment of each agent as a function of the profile of reported types. But in our setting, there is no payment rule. Okay? Third function is an inspection rule, specifies that a probability that an agent will be inspected as a function of the profile of reported types. So we have this. Okay? So in our setting, a direct mechanism consists of only 2 functions, the allocation rule and the inspection rule. Okay? Let me look just at the allocation rule for the time being. For simplicity, assume 2 agents. So I'm going to call little a the allocation rule, and so here's the notation. Little a subscript I of Ts is the probability that the good is allocated to agent I when agent, that should read agent I, reports T, and the other agent reports S. Yes?
Do we know that for a given argument, there is only one output for every allocation?
The answer is yes. So you're the planner. You get to decide this function. Right?
The function has only one output,
Which is in principle a probability distribution over possible allocations. Okay?
But since the allocation cannot depend on the outcome of the inspection, doesn't the inspection is worthless then?
No, so hold on. No, because you can condition inspection on whether in other words, if you think about it, I would only inspect you if I give you the good, right?
Okay.
Okay?
Sorry, so we're implicitly saying if you inspect and you find they lied, then you will be...
No, hold on a second. Yeah, so if I hand you the good and I decide subsequently to inspect, then I will withhold the object from you. Okay? So the answer is, since I haven't defined this inspection variable just yet, I don't want to answer that. So I said, let's just look at the allocation rule first. Okay? Okay. So what are the constraints the allocation rule has to satisfy? The fraction that goes to Mr. 1 when Mr. 1 reports type T and Mr. 2 reports type S, plus the fraction that goes to Mr. 2 when Mr. 1 reports type T and Mr. 2 reports type S, has to be less than or equal to 1. So notice I'm not insisting on equality, which means I have the option not to allocate the object at all. And finally, everyone must receive a non-negative fraction of the good. Does that make sense? Okay. Now, if you look at this, you can immediately see a problem, which is, if I'm going to write down a giant optimization problem with these as my variables, I'm going to have one variable for every agent multiplied by the number of possible reports, profiles of reports. So this means I get what looks like a ginormous mathematical program. Now it turns out it is sometimes convenient to look at another variable, and this variable is called an interim allocation variable. So it's calligraphic A, superscript I, subscript T. So you should think of calligraphic A as the expected fraction of the good that goes to agent I when he reports type T. And you can see that in the summation term on the right-hand side. Right? I'm summing up over all reports of the other agent multiplied by the probability that the agent has that particular type. Everyone with me? Now, in this definition, I'm implicitly assuming that the other agents are reporting truthfully. Right? Otherwise, this makes no sense. But just bear with me on that for the moment. Okay? So calligraphic A is the interim allocation probability. And I'm going to call an interim allocation probability will be implementable if there exists an allocation rule that corresponds to it. In other words, supposing I give you a bunch of calligraphic A's, I want to know if there exist little a's that satisfy that equation and this. Okay. Does that question make sense? So I'm going to hand you calligraphic A's, and now I want to know whether there exist little a's that satisfy this, this, and the equation at the top. Does that make sense? Now, why am I interested in this question? Well, I'd far rather work with the calligraphic A variables, because then I have one variable for each agent and each type, rather than one variable for each agent and each profile of types. Okay? So here's the goal: characterize the calligraphic A's. Okay? I'll make one more simplification. Let's suppose we restrict ourselves to allocation rules that are anonymous, meaning that they don't depend on the name of the agent. Now, in some settings, this assumption is benign. In others, it is not. Here is the theorem, and I've credited it to Borda, Maskin, Matthews, and Riley, and I'll explain why the four names in a moment. A set of calligraphic A's is feasible, is implementable, if and only if they satisfy this. Okay. Now, what is this condition? Notice, I have one inequality for every subset of types. What do I have on the left-hand side? The number of agents, the probability that an agent is of type T, the expected fraction of the good that goes to an agent of type T. So on the left-hand side, I have the expected quantity of the good that is reserved for agents whose types live in S. What do I have on the right-hand side? The probability that there is at least one agent with a type in S. Okay? Now, this is clearly a necessary condition for implementability. What is remarkable is that this is a sufficient condition. Okay? Now, if you look at this, you might say, how is this helpful? Yes, you've reduced the number of variables that you're working with, but you've just exploded the number of constraints. And the reason this is helpful is because this object on the right-hand side is monotone and submodular. Okay? So now, why should one be excited? Well, looking a couple of steps ahead, if you can write down your mechanism design problem as one involving maximize a linear function of the calligraphic A's, then it's maximize a linear function of the calligraphic A's over a Poly Metroid. And that we know how to do using greedy. Does that make sense? Okay, so this was originally conjectured by Steve Matthews, who proved it in a special case. Maskin and Riley subsequently generalized. In other words, they dropped one of the conditions in Steve Matthews' original paper. Borda gives the complete characterization. Okay? The proof that I'm going to give you is based on the max flow min cut theorem. Okay? Okay, so my goal is to prove this result to you. And the way I'm going to do it is essentially borrow something from Fourier and then finish the last step up with the whole matching theorem. Right? Stepping back a bit, mathematically, here is the question you're asking when you're trying to characterize implementable calligraphic A's. Supposing I give you this polyhedron in two sets of variables, x and y. And what I'm interested in is the projection of this polyhedron just onto the x-axis. There's the polyhedron P. What I'm interested in knowing is what is its projection onto the x-axis. Does that question make sense? Think of this as calligraphic A, little a. I want to project out the little a's and see what I get for the calligraphic a's. Now, Fourier tells us how to do this, essentially a variation of Gauss-Jordan elimination. So what you want to do is do row operations on this to eliminate the y variables, so that what is left is simply a system involving the x's. Does that make sense? Okay, so with the toy example, this is what I'm going to do. So assume that there are only two possible types, and so that you know when I'm talking about agent 1 or agent 2, I'm going to say agent 1's types are either T or T prime, and agent 2's types are S or S prime. Now, the first four inequalities you see are the feasibility ones. Total fraction of the good allocated should be less than or equal to 1. The four equations you see at the bottom are the ones that define the interim allocation probabilities. Okay? Now, what I want to do is from this system eliminate the little a's. How do I do this? I've got to multiply the little a's by appropriate coefficients so that when I add equations and inequalities together, they disappear. Yes?
Just for clarification, if you were under anonymity, you wouldn't need all four, correct?
That's correct. If I wasn't under anonymity, I wouldn't need all four. The only reason I put them back in was because I wanted to make sure that you see where agent 1 appears, where agent 2 appears. Okay, so here's what I'm going to do. Those first four inequalities, look at the first one, A1 of TS plus A2 of TS. I'm going to multiply by basically the probability of seeing that profile. Okay? So the first four inequalities, I multiply through by the probability of seeing that profile. And for the last four, I multiply by the probability of seeing that type. Now, the reason I've done this is you'll notice now that some variables that appear, some terms that appear in the top four now also appear in the bottom four. So that means I know what sorts of row operations to do to eliminate the little a variables. Everyone with me so far? Now, just to make this look nicer, I'm going to introduce new variables. xi of uv is fuv times fv multiplied by this. So remember, I've got these kinds of terms appearing everywhere on the left-hand side. Now, if you stare at this system, you should recognize it as the system of inequalities you get from the transportation problem. So think of the top half as supply constraints. So I have a note. So for every possible profile of types, agent 1 reporting T, agent 2 reporting S, I have a vertex. And I've run out of space for the fourth one. So the top 4 inequalities, I want to interpret them as supply constraints that say that the amount of flow that leaves those nodes cannot exceed what you see on the right-hand side. So here's a supply node, T comma S. What's the supply at T comma S? It's this. Okay. Now, if you look at those X variables, that tells you where the flow is going. Now let's look at the bottom 4. I want to interpret these as demands. So the demand at demand node little t is going to be this. Now this node is serviced by this. And that. Do it for all of these. And now what do I want to know? I want to know, when is this system feasible? And then if you remember the whole marriage theorem, it says this system is feasible if the following is true. Pick any subset of demand vertices. Look at all the supply vertices that serve those demand vertices. The total amount of supply must exceed the total demand. Right? And notice you have one of those constraints for every subset of demand vertices. That constraint, that's essentially the Borda, Maskin, Matthews, Riley's inequalities. Did that go by too quickly? Somebody said, does everyone seen the whole marriage theorem? Okay, so maybe I should talk about the whole marriage theorem then. Let's abstract away from this. I have a bunch of nodes which each have a certain amount of supply. A bunch of nodes which each have a certain amount of demand. What I would like to know is whether this supply is sufficient to meet everyone's demand. Now, if there is an edge between every pair of vertices, there's an easy way to check. Is the sum of the supplies larger than the sum of the demands? Agreed? But what if you don't have an edge between every pair of vertices? What if instead you have this? Then what's the condition you would need to ensure that there is enough supply to meet the demand? That's right. You would need that this is greater than or equal to this. This is greater than or equal to this. Okay? Now, supposing the network is a little more complicated. Well, certainly you need this to be bigger than this, agreed? Because this vertex cannot be served by anything but this. This vertex cannot be served by anything but this. So let's ignore these and let's look at these ones. What would the condition be? S1 plus S2 must be bigger than or equal to D1 plus D2. Does everyone see why that's the case? Now, do I need the condition that this is bigger than this and this is bigger than that? I certainly need this because this guy can only be served by this, agreed? But I no longer need this condition that this is bigger than this because this can be served by both this and this. Does that make sense? So now let's think about what's going on. If I look just at this vertex, I need this plus this to be bigger than that, agreed? Okay. But the problem is this guy also serves this. So you have to take into account the fact that this guy's supply will be shared possibly by two vertices. So you need a stronger condition that says the sum of these must be less than or equal to the sum of these. Does that make sense? Now, what's the general condition? The general condition would be pick any subset of demand vertices So pick any subset of demand vertices, look at all supply vertices that have at least one edge going to something in K, then the sum of the supplies must be at least as large as the sum of the demands. Okay? That's the whole marriage theorem. It says if that condition is true for every subset K, then there is a feasible way to match supply with demand. Yes?
So yes, you made it why that's necessary, but how is that also friction?
That's why it's a theorem. Right, but actually now you now have the machinery. Well, actually no. Let me take this back. So I'm simply appealing to the whole marriage theorem that tells me why this is also sufficient. Okay, and I'm using that theorem to say, well, that's how I eliminate the little a variables, because I can now write down the condition for feasibility in terms of this supply matches demand. Okay. And that condition, supply matches demand, when you throw out all the extraneous terms, gives you exactly the Borda, Maskin, Matthew, Riley's conditions. Okay? Now, the other advantage of this setup is that you can actually put in some additional constraints. So, for example, you may have constraints that impose quotas on how much supply can come from a particular vertex. Right? And it turns out that under certain conditions, there are natural generalizations of the whole marriage theorem that apply, even in those settings. So they export back to the auction setting, which means you can now talk about mechanism design problems with additional constraints, say quota constraints, on how much agents are entitled to receive. Okay? Okay. Okay, so now let's go back to the allocation with inspection problem. The variables I'm going to use are the calligraphic A's. Why? Because given a set of calligraphic A's, I know whether they're implementable. So I don't need to define the allocation rule directly. Here is inspection, and this should answer your question now, which is 1 minus C of t is the interim probability of inspecting a report conditional on the good being allocated. Now, what's my objective as the planner? This is the probability an agent is of type T. This is the value they enjoy if they get the good. And this is the expected fraction of the good that they receive. Right? So that's the social benefit. Less the cost. K is the cost of inspection. Now, I only inspect if you're allocated. And this is the probability of inspection. Does that make sense as the objective now? Okay. Now, what constraints am I going to impose on these? Well, I certainly need this to be feasible, but I know how to write those down in terms of a Poly Metroid. What are the constraints I need? I need this incentive compatibility constraint. So let's step back again. Whenever you define a mechanism, what you're doing is you're defining a game that the agents are going to play. That means you need a prediction of what they're going to play. And typically, we pick our favorite equilibrium concept. So in the background of any mechanism design problem is a choice of an equilibrium concept. I haven't picked one just yet, but there's an equilibrium concept. And we're going to assume that the agents will play that equilibrium of the mechanism. Okay. Now, then we invoke the revelation principle, which makes the following observation. What is a play? What is a strategy in this game? Well, an agent's private information is their type, and in this mechanism, they're only allowed to report a type. So a strategy is a mapping from their type to a reported type. So a strategy for an agent are these functions. Okay? Now, there'll be some equilibrium function. What I can always do is I can take my existing mechanism and wrap around it a proxy or a piece of software which will give you an incentive to report your type truthfully. How would I do that? I simply tell you, look, here's a piece of software that plays the equilibrium that you would play. So you might as well tell this piece of software your correct type. I'm now going to redefine my mechanism to be my original mechanism along with this additional piece of software around it. And that gives us the revelation principle, which says, without loss of generality, I can restrict attention to mechanisms where agents have an incentive to truthfully reveal their type. Okay? Now, when I set up the optimization problem, I have to recognize that have an incentive to truthfully reveal their type in terms of a constraint. And so here is the constraint. So the top inequality there is the incentive compatibility constraint. And it is on the left-hand side, I have got the expected value that an agent of type T enjoys if they truthfully report their type as being T. Now on the right-hand side, what do I have? Supposing an agent of type T says that they're type S instead. Now if they say they're type S, what is C of S? That's the probability that they're not inspected. Right? Because 1 minus C of S is the probability of inspection. Right? 1 minus C is the probability of inspection. So the right-hand side is the utility they enjoy if they pretend that their type is S. And incentive compatibility simply means that I want to give each agent an incentive to truthfully report their type. Everyone with me so far? Yes?
For the first inequality, do we need to multiply the left-hand side also by C of T?
Well, if you report truthfully, whether you were inspected or not, the outcome is you'll get the good, right? So whether you're inspected or not, the probability of you receiving the good is unchanged. Yeah? Yeah. Yes?
Are you already using that you can compare across agents?
I'm using that in the objective function. Right? So, as I said, this is the problematic assumption that as the dean, it is possible for me to, to make comparisons across departments.
Are you doing that cardinally? Or?
I'm doing that cardinally in this example. Yeah. It's cardinal in this example. Right? So I said, that's a problematic assumption, but as I said earlier, I want an example that's simple enough but also rich enough. And
you're assuming that they have unit utility for getting the good?
No. So I'm assuming that they have constant marginal utility for getting the good. Right? So the full, if you want, the full assumption spelled out is this, which is if you get utility T from getting the good, I, as the dean, also get that utility. Right? That's the assumption I'm making. So if you think about it, that's problematic because in some sense we're saying the preferences of the dean are completely aligned with the preferences of each department.
Now that I buy, I'm just thinking where the different utilities come from.
Okay, so not only am I assuming that that our preferences coincide, I'm also assuming, if you like, that it is possible to express utilities on a common scale. That when you say you get a value of, when sociology says they get a value of 5, and economics says they get a value of 7, I can compare those two numbers, right? That's the other thing. That's the assumption. Other assumption being made. Yes.
But some agents may not have one type, or
No. So each agent has a single type.
yeah, but is it possible that some agents are simply not allowed to have a type, so that the feasible type space is he
Okay. So in this setting, I'm assuming that everyone's type comes from the same set. But you will see in the analysis that nothing in the analysis depends on that. In other words, with the expense of added notation, you can do the same analysis by assuming that different agents' types are drawn from different sets. Okay, that's not going to make a qualitative difference. Yes.
Is it the case that you, the dean, can have different like Pareto weights for different departments, and it wouldn't mess up?
So the answer is I could. And so the way that would be reflected up there is I would have a weight multiplying. So now I have to be careful here, which is I can't use a mechanism that's anonymous anymore, right? Okay. So you could incorporate that, but at the expense of added notation. Okay. But the point I want to make is conceptually nothing very much is going to change. In other words, this theorem I gave you about Borda, Maskin, Matthew, Riley doesn't rely on the fact that types come from the same type space. It doesn't rely on the fact that the allocations are anonymous. Okay? Okay. The probability of not being inspected is between 0 and 1. And here, notice I have my Poly Metroid constraints. Okay. Now I'm going to do this informally because my goal is really only to show you how a couple of informal arguments are enough to give you a sense of what the optimal mechanism has to look like, and then it's simply accounting to go back and check that all of that's correct. Right? Now, if you didn't have the first two, you have a straightforward linear program, agreed? Maximize a linear function subject to Poly Metroid. So life is only difficult because of this and that. Does that make sense? Now, one other point I want to make, if you'll forgive me, this is because it peeves me whenever I see it, so I want to, so I always make a point of repeating it. The first constraint, incentive compatibility, is not a choice. You don't get to choose whether you have incentive compatibility in there or not. Incentive compatibility comes from the fact that we believe that the outcome of the game implied by the mechanism is some equilibrium. So if you talk about relaxing incentive compatibility, what you should be saying is, I have a different equilibrium concept in mind. Okay? So you should first come up with your different equilibrium concept, then talk about the constraint that you would plug in. Is that? Okay? Right, so I did. Okay. Now the first thing we're going to do is we're going to ask, does the incentive compatibility constraint impose any restrictions on the calligraphic A's? So in order to satisfy incentive compatibility, does that restrict the way in which you allocate objects? And the answer is going to be no. Right? And why is that? There's the incentive compatibility constraint. T's appear on both sides. I've simplified it, and I've got that. Now, that system of inequalities is actually not unusual in mathematical programming. If you stare at it, that system is, in fact, the dual to the problem of finding a flow in a generalized network. Okay, what is a generalized network? Let's start with a regular network. In a regular network, when you inject 1 unit of flow into an edge, 1 unit of flow comes out the other end. In a generalized network, when you inject 1 unit of flow in one end, alpha units of flow come out the other end. If alpha is bigger than 1, that particular edge is said to generate flow. And if alpha is less than 1, that edge is called an absorbing edge. Okay? Now, the reason these arise in practice is because if you literally think of these as flows through pipes, you can imagine that there is leakage or loss because of holes in the pipe. Then in that case, the alpha would be less than 1. If these networks represent monetary transactions, then injecting money in at one end is like putting money into an investment. and the money that comes out at the other end hopefully is more than what you put in which case the multiplier on that edge should be bigger than 1. Does that make sense? Okay. Now, it's not hard to see what kind of condition you need for feasibility of flow in these networks. Basically, you mustn't have, basically what you've got to avoid is that there are no flow generating cycles. So if there is a cycle of edges such that the product of the multipliers is bigger than 1, you have a problem. Why is that? Because if you inject a unit of flow in, what comes out at the other end of the cycle? More than 1 unit of flow. In effect, you've got a money pump. Okay? So money pumps are a bad idea, and so therefore we rule them out. Okay? And so if you go through the details of the duality argument, it basically says this system is feasible if and only if the product of the multipliers around every cycle is less than 1. Now, if you notice our C of t's, they were restricted to being less than 1, so clearly the product of any of them around any cycle has to be less than 1, and that means the incentive constraints impose no restriction whatsoever on the calligraphic A's. Now, those of you who've seen Myason's derivation of the optimal auction will know that there's usually an important step arguing that incentive compatibility requires that the calligraphic A's be monotone. That is not present here. Okay? Now, in some sense, that makes life harder because the set of possible allocations is now much larger. Again, let's go back to the incentive constraints, and let me rewrite it that way. Calligraphic AS is less than or equal to calligraphic AT over CS. So now let's, as I said, let's make some plausible guesses. Look at the lowest type. You're never, ever going to inspect the lowest type. If the cost of inspection is bigger than 1, it simply doesn't make sense to inspect anyone who says, my type is 1. Would you buy that?
The allocation rule was monotone.
Say again?
If the allocation rule was monotone.
If the allocation rule were monotone, you might buy that, but let's think about why this might be true. If the cost of inspection is bigger than 1, and you said your type was 1, then basically if I inspect you, I'm spending more than $1 in order to figure out whether I realize $1 in value. Agreed? Okay? So first intuition is that the lowest type will never be inspected. Does that make sense? Okay. Then if the lowest type will never be inspected, then C of 1 is 1. Remember, C of 1 is the probability of not being inspected. So what does that say? It says immediately that AT is bigger than A1. Look in the top inequality, put S equal to 1. Now, this is not monotonicity. What is this? This just says all types higher than the lowest type must get a higher probability of receiving the good. Does that seem plausible? Okay. Let's go with it. Then that means calligraphic AS is less than or equal to calligraphic A1 divided by CS. Does that make sense? So what I'm now going to do is I'm going to look at a relaxation, and I'm not going to put in all the incentive constraints. I'm only going to put in these ones. So AT is bigger than A1. C of t is less than or equal to A1 over AT. Now remember, AT is bigger than A1, so A1 over AT has to be less than or equal to 1. Agreed? And if I'm maximizing, how do I want to pick C of t? Well, if you look at the objective function, I want to make C of t as large as possible. So the obvious thing to do is set C of t equal to this. But we know that A1 is less than AT, So this is always less than or equal to 1, so I can just set C of t equal to that. That allows me to eliminate the C's entirely from the program. So now I have that. Okay. Now this is nicer because the only variables are the calligraphic A's. Maximize a linear function subject to Poly Metroid, and there's still one more annoying constraint. But this constraint is easy to handle. Set calligraphic AT equal to a bump plus A1. So in effect, I'm fixing the value of A1 and optimizing over the other variables. So plug that in. And then I have to take a bunch of stuff over to the other side, which looks like this. So I'll be interested in this function. This is still submodular. Because if I take a submodular function and subtract an additive term, the function is still submodular. Now the only catch is it may not be monotone. But if I control the size of the A1, I can ensure it's monotone. So I'm going to eliminate the A's and replace them by the X's, and I now have this problem. Let me make one more transformation. ZT equal to FT times XT. And that's my optimization problem. Now it is a straight optimize a linear function subject to a Poly Metroid. Now the first term in the objective function is a constant because that only depends on A1, and I said I'm fixing A1. Look at the terms on the other side. This is where the greedy algorithm kicks in. I pick the variable with the largest coefficient. What are the coefficients? T minus k. So I pick the variables with the largest coefficient and make them as large as I can. What do I do with the variables with a negative coefficient? I make them 0. Now, if I make one of those ZT variables 0, what am I essentially doing? I'm making AT equal to A1. So anyone with a type below the cost of inspection has the same probability of receiving the good as the lowest type. So intuitively, what's going on here? If the value you claim you receive is below the cost of inspection, I just randomize. Now, if you claim that you have a value for the good that is above the cost of inspection, then the probability of you getting the good goes up. How do I know this? The greedy algorithm. The greedy algorithm means that the allocations are monotone. Okay? So the higher your type, the higher your probability of getting the good. But what's also happening to the probability of inspection? It's also increasing, right? So notice, without doing any formal proofs, we already have a reasonable guess as to the qualitative forms of the optimal mechanism. So the optimal mechanism will involve some cutoff. If everyone reports a type below that cutoff, what does the dean do? Randomize. Right? If somebody reports a type above that cutoff, what does the dean do? The dean gives it to the agent with the highest possible type, but the probability of inspection goes up commensurately. Does that make sense? Okay. Now, stepping back a bit, why is this interesting? Well, one concern you might have at the outset is if you followed a simple rule of always giving the object to the agent with the highest type, that would encourage agents with low types to claim they have a high type. Agreed? Okay. Now, how could you discourage it? Well, one way you could discourage it is through inspection. Does that make sense? But that's not the only way. The other way you could discourage exaggeration is by reducing the probability of getting the good if you report a high type. Does that make sense? There are two possible ways I could discourage exaggeration. Either reducing the reward you get, in other words, reducing the probability of receiving the good, and I'm allowed to do that because there's no requirement that the allocation rule be monotone. Or I threaten inspection. Now both are costly. The inspection costs me K. Reducing the probability of giving you the good destroys value. Okay? So the question is, which of these instruments is better? And the Poly Metroid analysis tells me, okay, for high types, the better thing to do is simply increase the probability of inspection. Is that? Okay. Now, did I ever use really the fact that the submodular function was going to be monotone? The answer is no, because if it wasn't monotone, I'd replace it by its monotone cover. That would only affect that threshold, right? But the qualitative properties of the mechanism would remain the same. That there would be a threshold below which you don't inspect. Above the threshold, you allocate with increasing probability, but you also increase the probability of inspection at the same time. Does that make sense? Okay. Go ahead.
You first went to assumptions like you only inspect the people who get the allocation.
That's right.
Potentially you could consider other mechanism with other rules of inspection.
How would you punish them? But how would you punish? Suppose you expect that if they're not supposed to get the allocation anyway, how would you punish them?
Just deter.
No, so the thing is, so here I'm taking a shortcut by saying, because inspection is costly, I only want to inspect if I allocate the good to you. Does that make sense? Okay. Okay. Now, one other thing is it really crucial that all the types came from the same set? The answer is no. All that would, if the types came from different sets, you'd have a bunch of indices associated with each agent. And the only difference would be, for each agent, there is a particular threshold. Yes?
What if your cost of reporting is variable?
Okay, very good. Okay, so let me hold off on that and just okay. So the reason I did this example was because I think it shows, at least I was hoping it would show very clearly why knowing that it's a Poly Metroid problem would very easily lead you to the qualitative form of the solution. Okay? Now, the other reason I picked this was because here's an example where you're using an instrument other than money to compel people to report truthfully. Okay? And this immediately should generate in your minds, I hope, a number of other possibilities. So here I've assumed that inspection is perfect. Right? So what if inspection is unreliable? How would that change things? Here's another variation that a student, Rohit Patel and myself are looking at. What if you have access to both inspection and transfers? Okay. Now you'd like to know, when does it make sense to use transfers and when does it make sense to use inspection? Right? You can imagine other variations, and so now what was the variation you had in mind?
A variable cost, say for example, increasing in the reporting type.
Okay, very good. So in my example, the cost of inspection is borne by the planner. But if you think about my story about assigning a faculty slot, the cost of inspection could legitimately be borne by the department that is asked to go out and make a report and collect letters, right? And so notice that would change the incentive constraints because inspecting them would impose a cost on them, right? Now you can think of that as a form of a monetary transfer, but in some sense you're constraining the nature of the transfer. Okay? So if you like, there is, if you like, in the background a slightly more general question, which is, we can think of money sort of as the ultimate fungible way to transfer utility, but we might imagine lots of intermediate mechanisms that are less effective at transferring money. And then what would, what would mechanism design look like in such a world? Is that, yes?
Sorry, just one thing that you said when you answered in that case, wouldn't it just be, I mean, you just say there's some probability alpha, it would still be amenable to the solution.
Yeah, so my view is that adding the unreliable inspection shouldn't change things very, all that would happen would be the C of t would be scaled down appropriately by the unreliability of inspection. Okay, so other instruments beyond money are in some environments, inspection may only go in one direction. So if you think about income taxes, I may be able to detect if you underreport, but not if you overreport, right? So that restricts the kinds of deviations you could make, and then that leads to another set of issues in looking at mechanism design problems. Yes.
I have another variation in mind. I don't know if it's similar to what you already thought about. For you, inspection is a binary thing. Either you do it or you don't, and it's perfect.
Yes.
And it has fixed costs. What about from the application, I think you spend a little or less time on the thing, and then you have the probability of catching the guy. Is that equivalent when you just say probability of perfect inspection? You can just.
Okay, so I don't think so, because in that case, I think you're saying I get to choose the level of, in other words, I get to choose not just whether so one world is the inspection is either perfect or is perfect. The other is it's imperfect but fixed, right, at some level. And you're introducing a third possibility, which is I get to, at some cost, control the quality, the reliability of inspection.
The probability of catching the guy.
Yeah, so by spending more, I can drive down the probability, I can drive up the probability of correctly determining your type. So that I don't think, no, because then, I wouldn't be confident about the qualitative form of the solution, because now there would be another parameter that would matter, which you would have to say something about the marginal cost of, right, so you'd have to have a cost function, right? So as I put in more resources, the probability of detection goes up. And so the optimal solution should depend on the slope of that thing to a first order. Right? Yes?
Is it crucial that the set of types are finite?
Okay, so here I've used finite types, and the answer is no. And so I'm glad you asked that. I should say a little something about the business of discrete types versus continuous types. So the tradition in the mechanism design literature has always been to assume continuous type spaces. Right? Now, one parenthetical note, one of the earliest papers on optimal auctions actually started with discrete types. This is the paper by Harris and Ravi. Right? So, so is it better to have continuous types or discrete types? On this question, in a sense, I'm agnostic. You use whichever is mathematically convenient at the time. Okay? Now, my view is that any result involving discrete types is easily shifted over to the continuous type case. And at least for certain settings, I can give you a generic argument. And here's roughly how the argument would go. Supposing I solve the problem in discrete types, and I give you the allocation rule for discrete types. It's going to be a bunch of vertical lines, where on the horizontal I've got the type, and on the top I've got your expected probability of receiving the good. Right? I can turn this into an allocation rule for continuous types by simply doing this. Agreed? So I can take my solution for discrete types, and in the continuous type space, it becomes a step function. Does that make sense? Now, supposing you know that the allocation rules that you're working with have to be monotone, let's say because of incentive compatibility or some other consideration. Okay? As you make the width of the discretization finer and finer, you're getting a set of step functions. And what you want to know is whether those step functions converge to anything interesting. Right? Now, in general, they won't, because now we're living in the space of functions, and all sorts of things can happen in terms of sequences of functions. But there is a theorem of Helly, and this is not the Helly theorem about convex sets. This is another theorem, which says that the set of monotone functions is a bounded variation. Now, why is this useful? It says because of that, it means that if you have this sequence of monotone step functions, then there must be a convergent subsequence. Okay? So that's, if you like, a generic way of saying if you have the answer for discrete types, then just let the discretization go to 0, and you have the answer for continuous types. Okay, so what's the advantage then of discrete types over continuous types? And the advantage, I think, is it's much easier to make arguments involving linear programs than optimal control. Okay? With continuous types, you have to worry about whether the Pontryagin principle holds. You have to worry about when types are asymmetric. All of these problems I ignore completely when I work with discrete types and just take the limit. Okay? Now, should you take the limit in every case? My view is I don't see why there's a fixation on continuous types to begin with. You use whichever model is mathematically convenient. And now if you wanted a more principled answer would be, what does it mean to communicate a real number? Okay? So if you like that answer, stick with discrete types. Yes?
But do you think there are cases in which the continuous analysis actually won't translate to discrete space?
Okay. From the continuous to the discrete.
Yeah.
Okay, so I should be careful. My claim about the equivalence between discrete and continuous only applies to mechanism design problems. If I move outside of the realm of mechanism design problems, this is absolutely not true. You can find lots of examples where you get sort of odd equilibrium behavior when there are discrete types and when there are continuous types. Okay? So all you have to do is look at the literature on the existence of equilibria and first price auctions, and all of those difficulties arise because of the distinction between discrete and continuous. Okay? But with design problems, I don't have to use the mechanism that you gave me, right? I get to choose the mechanism. And so because you're optimizing, in some sense, you're choosing well-behaved mechanisms rather than mechanisms that drop from the sky. Okay? One other thing I forgot to mention is there's something else that the Poly Metroid formulation gives you. Because you know that the feasible set of interim allocation rules is a Poly Metroid, you have a description of all interim allocation rules in terms of priority rules. Right? Because the extreme points of a Poly Metroid are given by a priority rule. And those priority rules actually have a nice property, which is they actually describe dominant strategy mechanisms. So in some settings, for free, you get the following. If you solve the problem with Bayesian incentive compatibility constraints, and the optimal solution is one of the extreme points of the Poly Metroid, then you know the optimal solution can be implemented using dominant strategies. That's with no extra work. Okay? Yes?
Sorry, one last question about the discrete and continuous time space.
Yeah.
You said that it's the monotonic property of the function that allows us to...
In this case, yes. So, but really, I picked monotonicity.
Wouldn't the submodularity just be enough?
The claim is also, yes. So if I know that these calligraphic A's live in a Poly Metroid, then the convergence result also goes through in that case. Okay. So, but I tried to give what I thought was the most generic result possible, and the monotonicity one seemed the easiest. One last point. You may think that these Poly Metroid models are only useful for static settings. This is also incorrect. You can also use the Poly Metroid machinery to talk about dynamic mechanism design problems as well. Okay? Because there are certain classes of dynamic stochastic optimization problems that can be formulated as Poly Metroid optimization problems. Yes, good.
I wanted to ask about the dominant strategy implementation. Can you do that here because you have this random inspection thing, right?
So here I can't. So I should have been careful. That equivalence is true in the case when there are transfers. I don't know what the answer is in this case.
Right, because here it seemed like you're going to bind for C and
And so, yes, so yeah, so I don't know how to de-randomize the C's here. But the fact that there's a description in terms of priority rules is enormously useful, because it says in some cases I can restrict attention just to priority rules, and then the difficulty is just finding the right priority ordering. Yes?
So just to be clear, in the context of this problem, what would be a priority rule?
So in the context of this, so the priority rule is coming then basically from the T minus K's, right? So
Zero below the threshold. and
Yeah.
then wait.
Yeah. Now, there's something else subtle going underneath also, which is that at no point did I say that if your type is below the threshold, I actually allocate the good. I still may ration the good. That's still a possibility. Okay. So I'm out of time here. Thank you for your patience.